Welcome to ACS Webinars, bringing you the best and brightest minds in chemistry, live every Thursday at 2 p.m. Eastern. To view our upcoming schedule, please visit acs.org/acswebinars.
Everyone who's a synthetic chemist who's listening today will be familiar with Bruce Lipshutz. Dr. Lipschutz's personal history includes taking his PhD at Yale University with Harry Wasserman, and he did a postdoctoral stint with E.J. Corey at Harvard University. Bruce joined the Department of Chemistry at the University of California at Santa Barbara in 1979, and he's been there ever since. It really isn't possible to quickly go through the major research awards that Prof. Lipshutz has received, so I'm not even going to try to do that. Bruce has been a leader for a long time in the field of organometallic synthetic methodology. More recently, the research focus of his group has added a very large emphasis on green chemistry, recognizing the fact that the huge amount of waste that's generated in organic synthesis is perhaps the major challenge to sustainability of the global chemical enterprise. What Professor Lipshutz will present today is his work on the effort to get organic solvents out of organic reactions. To accomplish this, the Lipshutz group has introduced the concept of designer surfactants that enable key transition metal catalyzed cross-couplings and other related reactions to be carried out in water, most often at room temperature. So, Professor Lipshutz, the floor is yours.
All right, well, thanks, Joe, and my sincere thanks as well to both the ACS and the Green Chemistry Institute for this opportunity. So, as one might imagine, given the title of the talk, I have a big job ahead of me, trying to convince everyone to consider abandoning what we were all taught and we continue to teach in organic chemistry, and that is that reactions are run in organic solvents. But where does this come from? What's the history of using organic solvents, and why must we use them? I suspect that most people listening in are thinking, well, what does that mean? Obviously, we have to use them because our compounds are not soluble in water. But I would challenge that notion by asking everyone, when was the last time nature actually ran a reaction in THF? We have a pretty good sense about the history of organic synthesis, but not so much regarding organic solvents. Clearly, they began being used well over 100 years ago. Maybe it was benzene, maybe it was ethanol, maybe it was another solvent. But why did the brilliant minds of that time opt to use them when they really had the perfect model to follow? Nature. Nature's been doing chemistry in water for billions of years. And so I would argue that these scientists at that time, they may have made a big mistake. Can you imagine where we would be today had they started developing the use of water as the reaction medium? We wouldn't have this huge environmental problem we're now facing, since 85+% of the organic waste created by the chemical enterprise is attributable to one parameter, organic solvents. So when someone comes into your lab each week and takes your organic waste away, aside from the fact that you're probably delighted to get rid of it, where's it go? Is it burned to release CO2? Is it buried in some God-forsaken place while we pray that in another 100 years this waste doesn't come back to haunt our children and our grandchildren? So I would suggest then that the way we're now doing organic chemistry, it just has to change. It's not sustainable. It's even beyond our ken to imagine how much organic solvent is being converted each year into organic waste. So as Joe pointed out, my thesis, therefore, is that it's time to get organic solvents out of organic reactions. And so this discussion right now is really about vision. And that vision today is very easy to acknowledge. Indeed, everyone who goes into the organic lab has to make a decision. Which organic solvent am I going to use today? But I would argue that if we think into the not-too-distant future, imagine one walking into that same lab, and there's a bottle on the shelf, one bottle, and it's a bottle of water. But in that bottle of water is a little magic, and that combination allows one to run reactions with water-insoluble substrates, water-insoluble catalysts, and you get a bonus. You get to do it at room temperature. No external source of energy needed to be put into that reaction beyond that provided at room temperature. So how are we going to do this? Well, I would argue that most of us today are in what I would call a sort of traditional world using organic solvents. And of course, we've heard about the so-called alternative reaction media. And there are many of them, some which are listed here. And as important as all of these are to helping us transition from organic solvents to another media, I would argue that water is probably the most common denominator here. But of course, we can't use water to do chemistry, organic synthesis, especially room temperature, because things aren't soluble. We can't change those fundamental properties. So what we would argue is we need to create a new world. And I can tell you that in my past, people have oftentimes told me, you know, you're like in your own world. Well, maybe in this situation I am, because we would like to borrow from the traditional world of organic solvents and the use of water from alternative media and create a new world. Now, how are we going to do this? Well, we need to take a moment, a quick moment, and talk just about soap. And everyone here understands that soaps come in all kinds of shapes and sizes, and they're not the same. We can go down and buy a very inexpensive bar of soap from the local market, or we can go into some big-name store like Sephora and pay a lot of money. They're not the same. And so where do we learn about soaps? Well, we probably, back in our days in sophomore organic, were taught using one of the, let's say, more common textbooks. In a book of 1,000+ pages, there might be 1.5 pages devoted to soaps. And we're taught, as shown in the lower right, that these are salts of long-chain fatty acids. And they go into water and they form these spherical particles, which we're going to call micelles. That's pretty much where it ends, and so we go through life and we hear about all these terms like detergents, emulsifying agents, surfactants, and we think of them as being pretty much more or less interchangeable. But where do they come from? And so if we sort of think about that for a second, they come from all of these industries shown here that, well, what are they trying to do with soaps? They're trying to just get oil and water to mix. And so isn't it time, therefore, for synthetic chemists to develop our own surfactants that we can use to do sophisticated organic synthesis? And that's what we've tried to do in our first generation PTS, second generation TPGS-750-M, and third generation we call NOC. And what you'll notice here is that these surfactants are, in the Anastas and Warner sense, benign by design. Each one is simply an unsymmetrical diester, but the key component, the greasy component, the lipophilic component, is actually healthy. In this case, vitamin E, or a mix of steroids, mostly beta-sitosterol. And in fact, if one were to make this compound and just put it into water, one could literally drink it. It's just pro-vitamin E. It's equivalent to ester E, which is just, for example, an acetate. And all the ingredients here are usually GRAS-affirmed, generally recognized as safe. And in fact, for example, in this case here, beta-sitosterol, it's a cholesterol mimic. We actually pay for this phytosterol to be sprinkled on our Wheaties in the morning. So these are all essentially very healthy. Now, if you look at some of these, especially those with vitamin E, you might be thinking, well, these are known. For example, vitamin E TPGS has been known for many decades, put out, used in the pharmaceutical industry as an excipient. So if you have vitamin E in yours with a linker and a PEG, and vitamin E TPGS, known for decades, is exactly the same thing, and now you come up with this second generation, let's say, shown here, they sure look a lot alike to me. So what's new here anyway? Now, if you're in that frame of mind, that's exactly the point. You look at these, you think everything's got vitamin E, everything's got a linker, everything's got a PEG. What's the difference? Well, the reality is that's what's been missed by the world until now, because in fact, they're extremely different, and this can be shown very easily. For example, If we put each of those at the same concentration into water, put it on a grid, and freeze it, and take a picture using microscopy, so cryo-tem, what we see is that the vitamin E TPGS-1000 forms, in fact, 13 roughly nanometer spheres. But if we go to PTS, our first generation, we see a combination of spherical particles that are small, but a number of what we would call worms or rod-like structures, which are considerably larger, and the average, according to light scattering, is about 22 to 25 nanometers. But what we realized is that particles, for example, in our second generation surfactant, that are larger are much more effective in the chemistry because they present more grease, more molecules per micelle, and that it's absolutely crucial, particle size and also particle shape. And so they're not the same. But of course, most importantly, right, the fact is that when you take any of these, for example, based on vitamin E, and put it into water, those spherical particles on the outside containing the PEG interact with the water, solubilize them, and the chemistry is happening on the inside of the nanoparticle. This is homogeneous catalysis, in this case based on vitamin E, and the vitamin E goes together in a like dissolves like sense. And also keep in mind, there's very little of this material being used in the water. Usually it's on the order of 2 weight percent. So very dilute, very little of it in there. Essentially most of it is water. But keep in mind, water is not the solvent. The solvent is the inside of the nanoparticles. And so one can see now, if we just look at this relatively straightforward ring-closing metathesis reaction, done in water, room temperature, containing one of these surfactants, you can see the importance here that the PEG makes. Because in the TPGS series, meaning vitamin E, 4-carbon succinic acid linker, and by varying the nature of the PEG, whether it's MPEG, meaning methylated or not, is not important. Look at the variation that's possible. Simply by changing the number of units in the PEG, one can go from a 40% yield using the vitamin E TPGS, the smaller particles, to 88% using the larger engineered, newly designed surfactant. Based on that chemistry, it's important to recall, very important, that recycling is very much part of this scheme here. We designed these particles to be water-soluble and, in fact, to stay there. In these reactions, once they're done, there's no workup. Most people running these reactions in an organic solvent, you take it, you dump it into water, you extract, you do all these things. You're creating a tremendous amount of waste. That water is also waste. In this case, why would we do that? We're already in water. So we simply add a single organic solvent, we extract out the product, and we use the reaction vessel to do it again because these surfactants stay in the water. And so as you can see from this example here, after 10 recycles, there's no change. So let's continue then and take a quick assessment of what this is all worth. How do we go about quantifying the value of this in terms of green chemistry? And here we took the lead, as was suggested to us by John Tucker at Amgen, who suggested that we look at comparing our chemistry through the use of E-factors or environmental factors relative to what had been published by Big Pharma. And so we did that, and we published a review late last year where we looked at very commonly used reactions. And so, for example, we took a look at a Suzuki-Miura coupling shown here, and the pharma results are as indicated. And we're not going to focus on the fact that we could use potentially, under our conditions in water at room temperature, less catalyst, less ligand, and do it at room temperature relative to the need to heat. We're not even going to focus so much on the difference in yields, which are usually even better. We're only going to talk about then the E factors. And the E factors you see are defined by the end result. How much waste are we creating over how much product we're forming? And for the pharma industry, it turns out to be relatively high, usually between 25 and 100 kilograms of waste per product. And so for reactions like this, in general, what we find is that since we don't use any organic solvent as the reaction medium, our E factors for that parameter are about an order of magnitude lower. And if we include the water, which is not typically done based on the Sheldon, the original Roger Sheldon definition, even if we include it, again, we're down by about an order of magnitude. It's a huge difference in the amount of waste. And so we showed this for a number of different cases, and of course we have the opportunity, as noted earlier, to recycle our water. And when we start recycling the water, and notice we don't use very much of it. I mean, these reactions are usually 0.5 to 1.5 molar. So there's hardly any surfactant in there, there's hardly any water in there, and you get to recycle it. And then the E factors drop continuously to the point where it's just about how much solvent does it take to get this out, which you know, right, is going to be very little because you understand already the solubility of your compound in that solvent. So here are just a couple more examples, right? With Heck couplings, we can do the same. Again, focus on the E factors, very low in this sort of chemistry. So I think at this point, let's go on and take a quick sort of survey now of what one can do with some of this chemistry of late, and what are the lessons here from each of these types of reactions that we might be able to get from some of this chemistry. And so let's start with aminations because, of course, that's very dear to the heart of many people in the pharmaceutical arena. And some years ago when we were starting this process, I asked David Chung and Brian Rich to look at these aminations, and indeed, as we published back in 2009, it's a very nice way at room temperature in water of making carbon-nitrogen bonds to arrive, in this case, at unsymmetrical di- and triarylamines. More recently, however, Nick Isley and Sebastian DeBarco both published earlier this year that one can apply this chemistry to the maybe a hotter topic, which is the use of ammonia or equivalents in forming carbon-nitrogen bonds in aromatic and heteroaromatic systems. So indeed, using in this particular case the magic ligand turned out to be that from Takasako, shown in the upper right here, we could do these kinds of CN bond constructions very efficiently in water at room temperature. Now, we also applied this chemistry to heteroaromatic systems, and here we needed to increase the temperature between room temperature, in some cases up to 50 degrees, to drive these to completion. Nonetheless, the yields are very good. We could make sulfonamides, for example. We could do double substitutions to arrive at carbolines. And I should point out that very recently also the groups of Salome and Schmidt in Strasbourg have now published a way by changing the ligand to introduce alkyl amines onto aromatic and heteroaromatic systems. So that's very recent work which extends this to this other type of important coupling partner, alkylamines. We also, earlier this year, through the work of a fabulous postdoc, Sachin Honda, working with Dan Lippincott, and my colleague Don Owie, who did many of the calculations for this study, we can make carbon-oxygen bonds in the asymmetric series. And so here what we're doing is we're taking alenic acids and converting these into the corresponding non-racemic lactones. But the key take-home lesson here has to do with the catalyst. And what Sachin came up with, which was the notion that we could do this chemistry inside a nanoparticle, taking advantage of the fact that we have these very high concentrations and that the cations and the counterion ions, the anions, are therefore going to be associated. So if we have a non-racemic cationic species doing the chemistry but associated with it an anionic non-racemic counterion, that these ought to both influence the stereoselectivity. And that's exactly what happens. You try to do this chemistry in organic solvents, you don't get these kinds of selectivities. So this is a bonus coming from this sort of new world chemistry where we take advantage of the high concentrations and the associations of anions inside a nanoparticle. Now we don't have to do, of course, hetero bond formations. We have many opportunities to do carbon-carbon bond formations. So James Fenewald earlier this year also showed that he could, following the group of Phil Barron and co-workers, who first showed that one could introduce the trifluoromethyl group into heterocycles and heteroaromatics, we were able to turn that into what we feel is a greener process, do it in water, do it at room temperature, and under these high concentration conditions we need less reagent than the literature examples, and in all cases we could get results that are as good, or in some cases quite a bit better, than the published work. Carbon-carbon bond-forming reactions also apply, for example, to making olefins using olefin metathesis. And I chose this example here because, number one, it involves MVK, methyl vinyl ketone, which as a type 2 olefin is pretty challenging to get to do this cross-metathesis. But we're able to do that not anymore in chlorinated solvents, but in water at room temperature using the standard Grubbs 2 catalyst. But the key point here is, because we're in water and the exchange phenomena that are taking place, everything is exchanging, it's a dynamic system. And so things are exchanging micelle to micelle, but they go through the water. And if we drop, you see, the pH by just introducing a small amount of potassium bisulfate, the pH goes to roughly about 3. And what we find is that as the catalyst is exchanging between micelle to micelle, the phosphine is going to get protonated, and therefore the resulting ruthenium carbene, when it arrives at the micelle ready to do the chemistry, is coordinatively unsaturated. Well, obviously the rates go up. And that's why, for example, we can take, let's say, an overnight reaction and speed that up considerably, get that conversion and therefore yield to be higher. And we do this, in fact, even in a less expensive surfactant. Remember our third generation NOC, which of course was named after Piatira Klumpfu, right, who is from Thailand, and that's her name, and so we named the surfactant NOC. Now, the reactions appear, as you can imagine, at time 0, as shown. This is just a representative example. Honestly, they're ugly. They're just downright ugly. They look terrible. But if you have faith, and if you have good stirring, notice these are done in 5 milliliter microwave vials. You can do it in a 1 or 2 dram vial. Very important to stir vigorously. And over time, and not much time, you will find that reactions will tend to go maybe milky cloudy, maybe even homogeneous. So just with good stirring, you will see these initial mixtures, horrendous mixtures, turn into something that might resemble that. Okay, finally, from the standpoint of chemistry then, let's just talk about something that, well, people would say is sort of impossible. And that is to do Negishi cross-coupling reactions in water. That statement makes no sense because most people are aware that zinc reagents are especially water sensitive. You can't use a zinc reagent or a Grignard or something like that in water. You can't expose it to any water, let alone do it in water. And so you can imagine back some years ago when postdocs Arkady Krasovsky and Christophe Duplay came into my office and said they figured out how to do Negishi couplings in water. I did what any advisor would do. I threw them out of my office. And I said, you guys are out of your minds. Well, eventually they convinced me, of course, that this is quite possible. And all one need do is, in fact, take the precursors, no preformed organometallic, and just dump it into our surfactant containing water, some TMEDA, and our catalyst, and then add dirt cheap zinc dust or powder. And the key to this reaction, as is so often the case, was the ligand. And it was only, and still remains to this day, the Johnson-Matthey catalyst, the palladium amphos system, shown here, that's the magic catalyst that makes this chemistry happen. And so you can see, because it's zinc chemistry, it virtually tolerates everything, functionality galore, chemistry works very nicely, and again, all done in water at room temperature. And what's the concept behind all this? Why does this work so well? I mean, after all, how can we do water-sensitive chemistry in water? Well, first of all, we have to keep in mind that we're not doing it in water. We're doing it inside the nanoparticle, which is hydrophobic. And so what happens is that when we add all these ingredients, our substrates, our catalyst, TMEDA, things go inside these nanoparticles. But there's no chemistry that can happen. There's no organometallic. But as soon as one adds the zinc, collisions take place on the surface of the zinc, and the high concentrations of the starting materials now encourage zinc to insert, which it does selectively, into the sp3-based alkyl halide. That leads to a water-sensitive zinc reagent, but it's buffered by the micelle. So the TMEDA cleans the surface of the zinc. The water-sensitive zinc reagent is formed on the surface, and most importantly, if the rate at which all of that happens is such that it then goes inside the nanoparticle, finds the palladium and the coupling partner, of course that leads to the corresponding Negishi coupling. But the timing has to be right. And just like a beautiful Swiss watch with perfectly matched gears, if the timing is proper, meaning that the rate at which the zinc reagent is formed and enough time to go into the micelle, if it's formed too quickly, too many molecules are formed, it scoots out and it gets quenched. And so once that happens, Negishi couplings take place, and that's all possible inside the nanoparticle. Okay, so I think we are now where I would like to just quickly summarize by again challenging the listener. If you're still running your reactions in organic solvent, I would ask you to go back into your lab and pick any reaction that you have run and calculate your E factor. And I'm telling you now, it ain't going to be pretty, because you're going to come out with very high numbers. You're going to find out how much water, how much organic solvent you're using for the amount of material you make, and the numbers tend to be large. And can you imagine that being done at all levels, starting with sophomore organic labs on up to graduate students and postdocs training into the industrial sector? Now you see why there's so much waste being created. And so I would argue that there are alternatives here, as Roger Sheldon and co-authors put it. We'd prefer not to have to use a solvent, but think about water then as an alternative medium. And there are bonuses here, right? We're not heating these reactions, so many reactions create side products as a result of heating. And then for those of you in, let's say, process research where time in the kettle is absolutely crucial, we're doing it at room temperature. So there's no real time to wait for something to heat up to a refluxing organic solvent or to cool down at the back end. And it's in-flask processing. So you never have to have the stuff leave the reaction vessel after you've extracted out your product. So these are some of the benefits that we ascribe to this chemistry at all levels. So as everyone knows, I didn't really have much to do with this. This was really all done by the students that deserve the credit. I've tried to show most of them on the sides and bottom who were in the group at one time, as opposed to those who are here currently in the group. I absolutely have to acknowledge the financial support provided by both the NIH and the NSF for our programs in green chemistry. And then 3 companies that in particular have been very, very helpful to us, such as Johnson Matthey through Tom Collicott, who's provided palladium catalysts that have been mentioned, and many others that are part of ongoing programs. I really would like to thank Takasago and Hideo Shimizu in particular for sending us their ligands at a very good price, shall we say, and of course Sigma Aldrich through both Chris Thomas and Subir Garai, shown here, who in fact was part of the original team that brought us into green chemistry here at UCSB, for their continuing support of our programs as well.
Bruce, I'd like to ask you first a question from Larry Fertel. What about the issue of treating the water that's used after the reaction's done? So if the reagents and starting materials can't be placed back directly into the lakes and rivers, on a commercial scale, this could be a problem and expensive.
You know, this is the kind of question that I get oftentimes, and I guess my response to that is that we need to, of course, put this in perspective. What is the advance here? And I would argue that running a reaction in water, and very little of the water, together with the fact that the water can be recycled, of course, eventually it's going to turn into waste. But if you were to take, after 5 or 10 recycles, that amount of water and compare that to what one normally does now, given the E factors that are just based on 1 or 2 recycles, there's a huge advance here. So I think Larry is correct in the sense that eventually everything is going to be turned into waste, but the fact that we can recycle this water really gets us, I think, a step ahead. And at the industrial scale, the fact that you can reuse that water in the same reaction vessel, I think, is a huge bonus. So it's not perfect, but I think we've made some good steps in the right direction here.
Now a question from Edward Woodhouse. How long ago could green solvents have been widely used? Were there fundamental chemical understandings that have only developed in the past 10 years or so? Or were the barriers mostly based on habit and assumptions?
Yeah, that's a very interesting question. That may be more philosophical than factual, but I would imagine that, like so many things, it's a combination of both, right? So I suspect that in this case, certainly, and I find this as well, people tend to go with things they're familiar with, they're comfortable with, and so there are barriers, absolutely barriers, for people to get into something that takes them out of their comfort zone. And so there probably are, certainly there are new advances in terms of what we understand as newer green solvents, 2-methyl-THF and certain types of acetates and the like. So absolutely we've made a lot of progress, but there's no question that there are barriers here that are sort of just a question of familiarity, and I think it's important, as David Constable would certainly point out, that we find ways to overcome these barriers and get people more into thinking green.
Right. Saki Golafale asks, how can water be used to extract surfactants that are more hydrophobic and less hydrophilic, for example, pluronic 123, without using traditional organic solvents or heat to extract the organic templates?
You know, that is a question that relates to sort of what I would call inverted micelles, right, where you're actually putting the hydrophilic portion on the inside and the hydrophobic portion on the outside, and that encourages, therefore, the use of organic solvents to do exactly as he's pointing out, but of course that, to my way of thinking, is anathema, right? That's what I'm exactly trying to avoid. So I have to say quite succinctly that we just don't think along those lines, and we've never done any of that chemistry, so I don't actually feel competent to say.
Now, a question from James McNamara. For a large-scale reaction, there should be no need for an organic solvent for the extraction. The product should separate out from the aqueous layer, correct? And a little discussion around that is what he's asking for.
Yeah, Jimbo, that's exactly the case. If the products, and there are multiple ways to get compounds out, and I've only pointed out one possibility here, which is to do this sort of extraction. But as we actually published a paper earlier, I think it was this year or maybe late last year, about using mitoboronates and how in Suzuki couplings, oftentimes in the pharma area, products are solids. And what one does, therefore, is simply dilute the reaction mixture with, let's say, an equal volume of water. The product precipitates out, you filter that away. E factor, essentially, certainly in terms of organic solvent, is 0. And that water that you have then taken as the filtrate can be used again by simply augmenting it with an equal amount of the original 2-weight% of the surfactant, bringing it back to an overall 2-weight%, and then you just use the water again. And we did that multiple times as exemplified in that paper, and I think that you're exactly right. For solid products, there's no need to use organic solvent.
Stephen Hirsch asks, and you did deal with this question to a certain extent earlier, but he's asking, what's the yield on a volume of reactor basis? For other of these reactions, are they too dilute to be truly practical?
No, actually, I think as I mentioned, we run these reactions usually at a minimum of 0.5 molar. Now, that's a global concentration. And what we achieve by using micellar catalysis, and this is well known in that field, is that the concentrations inside those nanoparticles are probably on the order of maybe 10 times that. All of us would love to do organic synthesis and organic solvents at 5 molar, but we can't. But this is a way to do that. That's why reactions that might take 100 degrees in organic solvent now go at room temperature. The barrier to doing this chemistry is very low given the very high concentrations. So I would argue that that really is a key feature. That's part of thinking a little bit outside the box here. We're not used to running reactions at such high concentrations because it's physically not possible unless we can do it without solvent. But in general, we don't achieve that. Here we have very high concentrations. Remember, the water is just sort of forcing the aggregation of the nanoparticles.
Okay, I'm asking a question from James Stevens. He says, because the E factor of pharmaceuticals is large due to the large average number of steps that are used to produce a drug, if you were to use water in a 24-step drug synthesis, the E factor would still be very high. And please discuss that a bit.
Yeah, I think that's an excellent question also, because one could imagine that situation. It's a very important question. And I think what I did not cover, simply because of time, is that, remember, this same set of reaction conditions is applicable to all the suite of reactions that I showed you in one of the slides, and that's only a partial listing. In other words, we're doing the same use of the reaction medium for multiple types of chemistry. So that suggests that if you plan your synthesis accordingly, you will be able to do multiple steps in a single pot. And I can tell you in no uncertain terms that a large drug company, let's say, has already been able to document in a 7-step total synthesis that they can do 6 of those first steps in one pot, room temperature, using our technology at the kilo level. In fact, it's more than one synthesis, I've recently been told. So the answer to the question is that this presents an opportunity, whereas most people, you run reaction A, you work it up, you choose different conditions to do reaction B. We use the same conditions: room temperature, water, surfactant. And so one has the opportunity to do multiple tandem processes. And so that will dramatically change the amount of water that at the end of a 20-step synthesis you will have. So this is just the beginning. And I am sure that given so many creative people in chemistry, that there will be those who will come up with ways to use this technology in exactly that context, as drug companies are already starting to do.
This is a good time to fold in a question from Mike Berger. Does this work on a commercial scale?
Mike, I can tell you that, as I just pointed out, a drug company has documented this at the kilo level. I am not privy to the details. They don't consult with me in doing their drug syntheses. So to my knowledge, the answer is no. But we didn't invent micellar catalysis, right? What we invented or contributed is the notion that we can design our reaction solvents and use very little of it to maximize the outcome and derive all the benefits. Micellar catalysis is done on a metric ton scale every day in the industries that I showed you where they mix oil and water. So I don't think that's a problem, especially with an indication that at the kilo level one can do this chemistry. I think it's just a matter of time.
Okay, a question from Alan Doyle. Some chemists have Petri dish toxicology tests for new catalysts or for any product. What testing do you do or recommend for the chemistry that you're doing?
Okay, well, there are a couple of answers to that. I think number one is, of course, many industries have robotics, and I would imagine that in less than a day one could figure out which is the best surfactant to use, what's the best catalyst to use. I mean, that very sophisticated chemistry works to figure that out. I mean, these are just reaction parameters. This is methodology development that is really no different from what one does in a traditional sense. But I think one could take advantage of some of those techniques out there and probably zero in on the best conditions relatively quickly. What I will say as a final thought is that as we are trained to know what might be the best solvent, what might be the best catalyst in traditional organic solvents, that is not necessarily true in the case of inside a nanoparticle with this exchange phenomena going on. So this is an opportunity to be creative. It's an opportunity to develop new catalysts, as we are actually doing, that apply specifically to micellar catalysis at these high concentrations inside these nanoreactors. So sometimes the things that we think are the best ligands for doing an amination don't work necessarily well under these conditions. And so there is a process of discovery and evaluation. The rules are different. And that, to me, I find very exciting, because we get to take advantage as we discover these new rules. An example that I gave you was the use of lowering the pH of the water. We take advantage of the fact that we're in both worlds. Homogeneous catalysis inside the particle, water outside, exchange phenomena, take advantage of both.
A second question from Saki Golafali: is there a greener way to make amide bonds by direct reaction of amines with carboxylic acids?
Was this guy in my group meeting last night? Because the answer is absolutely yes. In fact, I'm not kidding you. This is exactly the topic that Chris Gabriel talked about. The answer is yes. We have that worked out very nicely. The manuscript is on my desk. I'll be reading that this afternoon and editing it, but the answer is absolutely yes. We are working with Sigma Aldrich and Subir Garai in particular on putting that out. And then the other part to this, and it relates to the former question as well, is that Aldrich will be coming out with these new kits. And these kits are sort of making it very easy for people to do this chemistry. It's going to be a kit that will contain in the appropriate reaction vessel a stir bar, the surfactant, everything that one needs to do this chemistry at a 0.5 millimole scale. All one needs to do is add the substrate. And so we are making these available as a convenience for people to try these reactions out. And then with regard to the latter question, there'll be 9 of these, apparently, what Subir told me actually yesterday. And then the number 10 kit that will be made available will be one to make peptide bonds in water, room temperature, using this technology. But they're waiting for me to publish the paper. So the answer is yes. It absolutely works very, very well, and we'll be describing that shortly.
Fantastic. I think we have time for one, maybe 2 more questions. Lauren Gaskell asks, are there any examples of using these designer surfactants in reactions on surfaces?
In fact, we did. We did attach one of our surfactants to a surface. We happened to choose, I think it was graphene. And we were looking for using that chemistry in a novel way, and we didn't really get much out of it. So I would say, to my knowledge, the answer is no. But I don't really feel that we have enough background to sort of competently give you a better answer than that. So as best I know, the answer is no, but it seems like wide open territory to me.
Gosh, we have a lot of good questions this afternoon. I wish we could go another 15 minutes, but this is probably the last one. Charles Palmer asks, have you considered the theory of hydrophilic lipophilic balance for determining how to optimize the PEG chain length?
Absolutely. That is the guiding principle, right? And that's exactly right. But we do try to do that balance, and you can see that vitamin E TPGS, the one from Kodak from the 50s, has a very high number, which leads to the smaller particles. So absolutely right. That's something we are very much concerned about. And it turns out that values that we achieve for our first, second, and third generation surfactants tend to be within a relatively narrow range. And that, we find, is what leads to the right size particles. And so that balance is crucial, because if the particles are too large, they drop out of the water, and that creates a new phase. If they're too small, we've already seen there's not enough through the exchange phenomena, grease left inside the particle to get enough of a binding constant for the chemistry to happen on the time frame we're all interested in. So that's one of the key parameters that led us to design, to engineer the particles to be in the 50 to 60 nanometer category. And that's right on. That's exactly right. That's a great question.
With all you've presented this afternoon, it's awfully hard to do, but I'm going to ask you to wrap it up with just a final thought. What is most important for us to take away from this presentation as the audience?
I guess I would claim that there are a number of items that I could hope to leave the audience with. For example, given the impact of organic solvents on the environment, the fact that we use so much, I mean, obviously I would like to encourage people to avoid using them if at all possible. Try to come up with something that's environmentally more friendly in which to do synthesis, and we've seen some of the alternatives that are available, and what we have, that's of course being one of them. I think also people should appreciate that we're doing something different here than traditional synthesis, in the sense that we have access to these high concentrations in these nanoreactors. And that allows us to get the temperatures down. Reactions tend to be very clean, and that can simplify the workup. If you have a problem, for example, with impurities, you may not get those impurities doing this type of chemistry. And then also, I would say in general, try to minimize the amount of water in a workup. I mean, in our case, of course, we only have the reaction mixtures. We don't add any water. But people tend to dump these things into water, and that ends up being waste. And it's got to go somewhere. It requires special handling and disposal, as people have already pointed out. Another important point is that micellar catalysis presents a very unusual opportunity. People can design your own solvent. That's what we're doing here. I could imagine people all over the world coming up with their own choices as to what they want to build in to the lipophilic part of a nanoparticle, which is best for your chemistry. Think about it. You can design your own solvent. And then finally, I guess I would also, just as a final thought, I think it's important for people to think about this outside the box. In other words, consider the impact of your reaction, the reaction medium that you're choosing, the environment here, and be open, right, to what the alternatives are out there so that we could all contribute to sustainability.
Thank you for watching this presentation. ACS Webinars is provided as a service of the American Chemical Society as your chemistry source for live weekly discussions and presentations that connect you with subject matter experts and global thought leaders concerning today's relevant professional issues in the chemical sciences, management, and business.